Okay, today's lesson is going to be on radioisotopes and radioactivity, as you can see from the title. Um, we've already looked at isotopes. We've seen many examples of some isotopes, and I'll just remind you of a couple of them. The other day we looked at something that would have been called a carbon 12, all right? Carbon 12 with an atomic number of 6, and a carbon 14, right, with an again atomic number of 6. And if we take a look at the particles in these two isotopes, here we've got in terms of the number of protons, there's 6, and then the number of neutrons, remember we have to subtract, right, there's 6 as well. And in terms of electrons, and we're not really worried too much about electrons here in this particular lesson, there would also be 6, all right? But in this case, because we're talking about isotopes, remember, isotopes have the same number of protons but different number of neutrons. So if we take a look at this one, the number of protons, again, that is determined by the atomic number, 6. And if we take that 14 and we subtract 6, then the number of neutrons is 8. So here we have two different isotopes of carbon, one with 6 neutrons and one with 8 neutrons. All right, and that makes them isotopes. Now, I guess the question is, what is a radioisotope? And you've probably heard of radioactivity before as well. And at this point in the lesson, if I were here, I would ask you students what you think of when you hear the term radioactivity, right? And I get lots of interesting answers. People talk about fish with 2 heads and all kinds of, and radiation, right? And emissions and things like that. And obviously we also get terms like cancer, right? Because you're all aware that radiation and radioactivity can be cancer causing, all right? Some people even come up with things like treating cancer, right? If somebody has radiation therapy, they'll be using radiation to treat, cancer. So those are all good things, except like the 2-headed fish. That's a very rare scenario. But anyway, let's talk about what causes this radioactivity and what radioactivity really is, and how that relates to this thing that we call radioisotopes. All right, so let's jump ahead here and let's put some definitions down. Again, I'm going to go quickly so you can go back and write the note from the PowerPoint presentation. We already know that many elements have 1 or more isotopes, but in this case, what we're saying is some of these isotopes are unstable, all right? Atoms of an unstable isotope decay, emitting radiation as their nucleus changes. And we do use the term decay here, but the term decay is not like you might have learned in, say, an ecology class about like a log decaying in the forest. That is not what we mean by decay here. The term decay is used here because of the mathematical way in which the radiation decreases, and I will show you examples of that later on, all right? So we say that the isotopes decay, but they're not like getting old and breaking down. They're just changing, all right? And they change by emitting radiation as their nucleus changes, all right? So if an isotope can decay, if it's unstable, as I said up here, then we call it a radioisotope, and we say that they're radioactive, all right? So those are the terms we use. Excuse me. So again, what is meant by unstable? We're not talking about, an unstable, again, that's a tricky one. We're talking about energetically unstable. That's a tough one to describe. I can describe unstable in terms of energy by simply kind of giving a couple of examples. Let's say that there was let's say we got a desktop, like a table here, and I've got a box on the table, and the box has, dimensions like this, all right? And if I were to push on this box like this way, right, there is a chance of that box falling over like this, all right? In physics, we would say that that box is in an unstable position, all right? Its center of mass right here is so far up above the ground, right? It's got a certain height here above the ground. And if we were to push this thing over, we could get the box to kind of sit sideways like this. And what that does is it makes the center of gravity now a little bit lower. It brings it closer to the ground. And we would say that this one is more stable, all right? More stable, all right? It might even be in the most stable position. And we would say that this is unstable, all right? Unstable. So things in physics, if they have a lot of energy in them, in this case it's got gravitational potential energy, it means that it has the ability to fall down. If it has a lot of gravitational potential energy, we can say it's unstable. It's unstable with respect to gravity. If we can then make it fall to a lower height, all right, call that H2, then we can say that that object has fallen down and become more stable. So now if I try to push on this sideways, it can't fall any lower. So all this thing is going to do is slide, right? So it'll just slide along the desktop instead of falling over, all right? And a nucleus can also be stable, but not like a box, but like can be made more stable by bringing the particles of the nucleus closer together, all right? Can do it by shifting particles around. So if I have an unstable nucleus, it means that there's something in the nucleus that is energetically too high. And it's going to do something to make it go to a lower energy, all right? So a radioisotope has, it's almost like it's got too much energy in the nucleus, and it will do something to result in a more stable nucleus. And what it does is it emits radiation. It spits something out, and it makes it more stable, all right? So that's what a radioisotope is. It's unstable, it's going to give something off, and it's going to try to become stable. And it has been determined that there are three main types of radiation. If I can click to advance, I'm struggling. Let's try this. There we go. And it has been determined that there are three types of radiation. You can see here on the top of this slide, it says alpha particles. Let me just swap over here. Let's get a new page. My computer is running slowly. Let's talk a little bit about the three types of radiation before we go ahead and define them. I've already mentioned to you a scientist by the name of Ernest Rutherford. He shot alpha particles at gold foil to discover the nucleus, a very important thing. Excuse me. And where did he find these alpha particles? Well, in the late 1800s, a scientist by the name of Marie Curie, and I'm sure you know Marie Curie. Let's take a look here. Curie. Nope, I gotta have another R. Curie. Let's try Marie. There it is, Marie Curie. There we go. A scientist by the name of Marie Curie, along with her husband Pierre, there's Pierre right down here, were working on newly discovered elements and isotopes that were somehow giving off these emanations, all right? They were giving things off. And Marie Curie was a chemist who was kind of responsible for purifying these substances. Now, she didn't realize that the radiation that was being given off was very dangerous. And in the end, she ended up passing away from radiation sickness because she worked with this stuff for years and years and didn't realize the dangers of it. So Marie Curie helped kind of strengthen or concentrate chemicals that had this ability of being radioactive. Now, that brings us back to Rutherford, all right? So what did Rutherford do? Well, once scientists started to have access to these radioactive materials, And in the beginning, it was likely uranium, all right? There could have been some other materials that they had found, polonium, et cetera, And again, they like to put these radioactive things in a box. Typically, that box was made out of lead, so it would absorb all this. And so again, there's radiation emanating in all directions out of this thing. There's particles coming off of it, and with a hole in the box, they could have the particles come out nice and straight. Now, what Mr. Rutherford did then was he took a big magnet, all right, so a big bar magnet there, and put it around the beam, so I'll put it north and south. And what he discovered was when he did that the beam spread into three main beams. So one beam went this way and had a tight little spin, another beam went straight through and didn't do anything, and a third beam went around the corner here and did it at a glancing turn. And in the end, this first beam that he discovered was made out of a helium nucleus, all right, nucleus. And being the very creative scientist he was, he wanted to give this first beam that he discovered a name, so he called it alpha rays, all right, or alpha particles. Actually, particles is better than rays. Alpha particles. And in the Greek alphabet, alpha is the first letter, so being creative, he called them A particles. And he's really not that creative, but still, alpha, that's what we call them. And the second particles he found, which bent the other way, all right, again, being very creative, he called them beta particles, and again, being very creative, beta is the Greek letter for B. So yes, essentially he called them A and B. So, okay, so he's a physicist. He's not very creative, but that's okay. So we've got alpha particles and beta particles, and it turns out that the beta particles are electrons. And we've already seen the electrons, all right? They were in the Crookes tubes. So these radioactive elements are giving off sometimes alpha particles, sometimes they're giving off beta particles. And then the last beam that went straight up the middle was harder to discover, and these are called gamma rays, all right? Gamma, you might think, is the letter G, you know, in the Greek alphabet, but it's actually the third letter in the Greek alphabet, so it's the letter C. So yeah, he called them A, B, and C. Oh well, no marks for creativity, but good marks for science. So he found these three different rays. He ended up using the alpha particles to discover the nucleus. But let's now talk a little bit about what these three types of radiation do and how they behave. Okay, so let's go back to our note here. There we go. So let's write a little bit of information down about alpha particles. Again, when you run through the PowerPoint, you'll have a chance to write these down. They're helium nucleuses. This doesn't say he, like a boy, He, helium. Therefore, they're made up of 2 protons and 2 neutrons. And so if we have the symbol for them, it looks like this, He, mass number 4, atomic number 2, right? 2 protons, 2 neutrons. And why would a radioactive element give off an alpha particle? Well, it turns out that if an element has too many protons, all right, when it comes to the nucleus, a nucleus is most stable when it has approximately the same number of protons and neutrons. And it likes them in pairs. I can't explain to you why. To be honest, I really don't know exactly why. I've read some stuff on it, but let's just say that when they've got similar numbers of protons and neutrons, they're stable. So if we take a look at something like uranium, an atomic number of 92 protons, and a mass number of 238, it doesn't take a quick subtraction of approximately 100 to realize that, you know, we've got about 130, 140 neutrons in here compared to 92 protons. That's an unstable situation. So what does an unstable uranium do? It spits out an alpha particle, all right? And now let's figure out what's left here, all right? So when we figure out, or when we do a calculation involving a nuclear reaction, it's really easy to figure out what you got left because we need to have the same mass at the end, in other words, the conservation of mass. So if I've got a mass of 4 removed from this mass of 238, I'm going to end up with 234. And if I have a charge of 2 protons removed from a nucleus that has 92, then I'm going to have 90. And now we can go to our periodic table, and I don't have a periodic table up. Let's see if we can find one. Let's back it up there. Periodic table, all kinds of them. Let's take a look at that one. We like that one from the last lesson. All right, so let's view the original. All right, so if I take a look over here, I'm looking down here at my uranium. There it is right there. Now I've lost 2 protons, 1, 2. I'm to 90. That is a thorium. All right, so let's go back to our PowerPoint here. What's going on here? That's not what I want. There we go, which means I have here a thorium. All right, so that's a simple way to balance a nuclear reaction. That's an example of an alpha decay. It literally spits out a little chunk of its nucleus, and a new nucleus is left. All right, so the atom literally changes into a new type of atom with a little piece flying out. And it's this piece flying out that's the dangerous part, right? These little pieces can run into other atoms and cause them to knock out some electrons, or maybe even knock out some protons and neutrons and change those atoms. And if those atoms happen to be in the DNA of a cell, those atoms changed in the DNA could cause a bad mutation, a bad change, and that can cause cancer. So that's how these radioactive particles do their damage. They can run into atoms in the DNA of a cell and cause trouble. All right? So that's an alpha decay. Let's take a look at beta. All right. So beta particles. Beta particles are negatively or positively charged electrons. And yes, you heard me right. This is probably the first time you heard of this. Positively charged electrons. The positively charged electrons are called positrons, and I'll talk a little bit about positrons in a moment. So here we have a symbol representing an electron. We're going to write it as if we're writing an atomic notation. So an electron isn't really an atom, but we can write its symbol down, E, and it doesn't really have protons, but it has a negative charge. So in the place of atomic number, instead of writing down the protons, because there isn't any, we can write down the charge. So really, let's think of this bottom number now as thinking of the charge number instead of the atomic number. So we now have a charge number of -1. The electron is really light. Remember, it's like 1/2000th of a proton. So it essentially has a mass of 0. So we represent an electron with an atomic number, right? Essentially its charge number, -1, and a mass number of 0. And if we're talking about this strange positively charged electron, it has a charge of +1 and a mass of 0, all right? And I'll talk a little bit more about these two guys in a second. Let's take a look at an example of where a beta particle can result. So if we take a look at this hydrogen with 3 mass, right, 1 proton. So it's got 2 neutrons and 1 proton. It's got more neutrons than protons. Remember, I just said atoms are the most stable when they've got about the same. So this is unstable because this hydrogen atom has 2 neutrons to 1 proton. So what it will do is it will eject a beta particle. It will eject an electron right from the nucleus, which is also a strange idea. We thought electrons only existed in orbit, but they can actually be ejected from the nucleus. If we do the math, 3, 0, I need the mass to be the same as it was at the beginning. So the mass is still 3. Charge, and my charge has to be conserved as well. It can't just disappear. So if I've got +1 on the left, and then I've got a -1 here. Whoops, I didn't mean to write that. I was just circling. If I got a +1 on the left and a -1 here. What do I have to put here to get a number of +1? Well, I need 2, because 2 plus -1 is 1. So what atom does that get me? Well, now I need to look up my atom that has an atomic number of 2, and you'll take a look here, atomic number of 2, helium, there it is there. So let's switch back here. So that's, and I'm going to lose my writing for some reason. There it is. And that turns that into a helium. Okay, so let's think about what happened here. Whoops, it's terrible E. In this case, what happened? The neutron spit out a little negative chunk and turned into a proton. There's that little negative chunk. So that is a beta emission, okay? Let's take a look at one that produces this positively charged electron. Okay, let's move on to the next one. Oops, come on, computer, behave. All right, so let's take a look at this one. In this case, we've got beryllium, mass number 7, atomic number 4, 4 protons, 3 neutrons, more protons than neutrons. Again, unstable. So let's take a look. In this case, a positive chunk, let's put a little positive there, is going to be emitted. Again, 7, 0, 7. 4 plus 1, it has to add up to 4. I need a 3. Let's look at what we're dealing with here. 3 means I have a lithium. Okay, so the beryllium has been turned into a lithium. So what happened here? In this case, too many protons. A proton spit out its little positive chunk, like it spit out its positive piece, therefore turning it into a neutral particle like a neutron. So in this case, a proton became a neutron when a positron was emitted. All right? Let's just have a little talk a little bit about what this positron is. Okay? In the 1930s, a new science was kind of being discovered, theorized, kind of not created, but the rules were kind of being laid down, and it was called quantum mechanics. And a scientist by the name of Paul Dirac, let's go back here, show you Dirac. Let's take a look at Dirac. Dirac, oh, smarten up, you silly thing. Here's Paul Dirac. He was working with the equations, and here we got all kinds of equations, and this is kind of interesting, but this isn't the equation he was working with, but he was working with the mathematics that was being discovered that we call quantum mechanics. There you can see there quantum mechanics. And it turns out that as he was using the equations, at one point in time, he had a part of an equation that kind of looked like, oh, why are you not writing anymore? Click here to restore the writing. He had an equation that kind of looked like this. He needed to take the square root of say, the mass squared, okay? So he had the mass of an object that he needed to take the square root of. Now, if you recall from your mathematics, if I were to take the square root of m squared, I would get m. But if we really think about it, I wouldn't just get m, but I'd get plus m and minus m. Now that's an interesting situation. Scientists believe that mass was just mass, that something that had matter was just, an object like that we know that has space and takes up, and has mass, right? Has weight. But with this equation, not only was there regular matter, right? We'd say the positive is just regular matter, all right? But there was this negative stuff, which is like the opposite to matter, the negative of matter, which they called antimatter. All right? So theoretically, he predicted the existence of this antimatter. And it wasn't long until scientists went looking for this stuff that they found that there was this opposite to regular matter, which we call antimatter. Now, what is antimatter? Well, antimatter is literally the opposite of matter. Just like if I take a positive charge, right, and I add a positive charge to a negative charge, right, I get something that's neutral, right, which I spelled wrong. I need something in there. Neutral. If I have something that's made of matter, let's say I have a regular electron, and I add it to an anti-electron, which is also known as a positron. All right, what do I get? Well, they cancel each other out. Their matter literally cancels each other out. Now, you think you would get nothing, but what you do get out of that is lots of energy. All right, lots of energy comes out. Big explosion when you put matter with antimatter. The reason you get energy is because Einstein has an equation that's E equals mc squared. And if you were to cancel out the mass of this stuff, all right, all that matter would be turned into energy, and that's where that energy comes from. All right. If you've seen a movie called Angels and Demons, there's the bad guy that had some antimatter and it exploded and made a lot of, made a big bang. Now, it wouldn't work like that, but it would actually literally annihilate each other. So when you're done, when you put a little bit of matter together with some antimatter, you can actually cancel them out. And not only are there anti-electrons, but you could have an antiproton, all right, that has a negative charge. You could even have an antineutron, but an antineutron also has a neutral charge. But if you put together an antineutron and its regular neutron, it would still annihilate each other. They're opposite matter. You actually could put an antiproton in a nucleus, and you could put then an anti-electron around it, which is a positron, a little positron around it, and you could make what is called anti-hydrogen. And they've done that. They've recently done that. They've been able to make an anti-atom, all right? So that's what antimatter is, okay? And it's a real thing. One of the great questions of physics is, why is there more matter than antimatter? Like, why don't we, when we're walking down the street, run into somebody made of antimatter and then, like, annihilate each other? Like, that doesn't happen. So that's one of the mysteries of science. What happened to all of the antimatter? Why don't we have more of it around? Anyway, so here we've got a little silly joke here. I hear that scientists have now made anti-hydrogen. My question is, if you mixed anti-hydrogen with anti-oxygen, could you make anti-water? And in theory, you could. And if so, could it be used to start fires rather than put them out? And the scientist thinks. And it says, Dear Curious Sam, unfortunately, Dr. Science is unable to provide you with a response to your recent query. I think your question may have hurt his brain. All right, you may now giggle slightly. All right, let's continue. Okay, so what have we got here so far? I'm actually going to back up here for a second. So I've lost the writing here, but here we've got a positron emission. And here we've got a regular electron emission. Those are beta particles. And then we have alpha, which is the helium nucleus. The last type of radiation is what we call gamma radiation, and that's that last one. Now, gamma radiation is not a particle. Gamma radiation is a type of electromagnetic radiation, which is essentially light. All right? It's really high energy light. High energy. All right? It's very, very penetrating. What do I mean by high energy light? Let me just show you here for a second. Let's get a new page. All right. If we take a look at all of light, all right, and I were to make like a line here across here, and in the middle I put here what is called visible light. That's what we can see, all right? Way down here at low energy, we have what is called radio waves. Radio waves. They make our radios work, all right? And a radio antenna at a transmission station would send out radio waves, and your radio would catch them and you'd hear them. Radio waves don't hurt us at all. Next thing we have here after radio waves is a region that we call microwaves, all right? Microwaves. You might think microwaves are dangerous, but it's actually one special color of microwaves that cooks things. Most microwaves aren't dangerous. And actually, over here in the microwave region, down here in this end, this is what cell phones use. Cell phones. So your cell phones actually give off microwaves when messages come in and go out. All right. Some people think that that can be dangerous. There's lots of studies that are being done to determine whether it's dangerous or not. But we're not worried about that right now. After microwaves, we have something that's called IR, which is infrared. And infrared is essentially heat. All right. So if you've ever seen a picture like a heat picture, what they're looking at is the infrared. Now, the visible starts with red and ends up in violet in what we would say is Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet, right? And those are all the colors of the rainbow. And that we can see. Now, here's where we're getting into the high energy light. And high energy can be dangerous because that light can do things to other atoms. There's enough energy in them to knock electrons off of atoms and change the nucleus and do all kinds of things. Up here, we've got what is called UV, ultraviolet. You've heard of that before. It gives you sunburns, right? It gives you sunburn. Can be dangerous. Beyond UV, we have something called X-rays, right? X-rays are X-rays. They can go right through your skin, but you can't go through your bones. And so when you get an X-ray done, you can see the bones and you can't see the skin. It goes right on through. Now, higher than X-rays, we've got gamma. Gamma is the highest energy light that exists. It can go right through skin and right through bones and can do all kinds of damaging things. If that gamma ray were to run into a nucleus of an atom in a DNA strand in a cell, it can cause a mutation. And as I said, with the other radiation as well, it can cause cancer, right? But it can also kill cells. It could kill cancerous cells, right? If someone that you know is having radiation therapy, right, they would be using the radiation that comes off of those atoms. So let's put someone here that would be our cancer person, and let's give them a tumor. Give them a tumor right there. That's a tumor. And if they want to kill that tumor, they'll shine a bunch of gamma rays on it. The problem is if you were to shine gamma rays all over this person's body, you'd kill all the cells. That'd be no good. You'd cause more damage than good. So here's the trick they use. What they'll do is they'll take a picture of where the tumor is, and then a computer-guided machine will fire a gamma ray such that it goes through the tumor. Now you can see here it's going through other parts of the body, but the machine then will rotate, and it will go through the tumor again. And I'm not doing very well at this. The machine will rotate, go through the tumor. The machine will rotate, go through the tumor. I'm doing terrible at this. The machine will rotate and go through the tumor. Okay. So what happens is many, many weak doses will result in a concentrated dose on the tumor, killing the tumor cell, but leaving the rest of the cells hopefully relatively undamaged. All right? So that's the way gamma rays can be helpful. All right? So gamma rays come from nuclear reactions. All right? I'm getting there. We're getting there. Here we go. And so they're a type of light, right? They're exactly like visible light, but with a much higher energy, shorter wavelength. And the emission of gamma rays don't result in any changes to the mass number and the atomic number. It just makes it more stable. I think of it like, you know, if you put a bunch of styrofoam pieces in a bag, if you wanted to get more in, you could shake the bag and make the styrofoam pieces kind of get together and make a lower, smaller volume. That's kind of like what's happening to the protons and neutrons in a nucleus that is unstable and gamma radiation is given off. It's like the nucleus is readjusting the positions of all the pieces so everything can get a little more closer. And when it does, it gives off a burst of gamma radiation. All right? So there is the third type of radiation. No equation needs to be done because the nucleus doesn't turn into something new. Okay, where am I at? There's some information about the way the nucleus, or sorry, the types of radiation work. So here, they're relatively slow, but they're heavy, the alpha particles. They can only go a few centimeters in air until they run into some air particles and stop. And a piece of paper would stop alpha particles. Really, you can stop an alpha particle pretty easily. Beta particles go relatively fast. They're faster. They can go a few meters in the air until they run into some other atoms. And 1 or 2 millimeters of metal will stop them. But gamma radiation is incredibly penetrating, very fast, speed of light. Penetration in air can go right through air, and it takes about a meter of lead or concrete to stop them. And that's why our nuclear power plants are built inside these great big concrete domes to keep the gamma radiation from getting out so that it is absorbed. Okay, I'm not going to teach you about half-life right now. I will do that in the next lesson, and you can finish off any previous homework or lab work that needs to be done at this time.